My name is Zeev Zalevsky. I'm from the Faculty of Engineering at Bar-Ilan University in Israel. Before speaking of how to improve resolution, let us understand what exactly resolution is. So resolution is defined as spatial feature that an imaging system can resolve. Now, it is very important to emphasize that resolution is related to space, to define a spatial feature that we can capture. While an imaging sensor can capture information not only in the spatial domain, but also in time domain, in color domain, in polarizations, and so on. And as you are going to see in my following slides, we're going to use this availability of capturing information in other domains in order to enhance the resolution in the space domain. Now, there are three factors that limit resolution in optical imaging systems. The first factor is the factor of diffraction, as it was defined by Rayleigh and Abbe. The second factor is related to the geometry of the detectors that capture the images. And the third factor is the noise level, the signal-to-noise ratio at every pixel of our detector. Let us briefly go through this. The diffraction limitation is actually limited by the F number, or it is related to the numerical aperture. Numerical aperture is 1/2 F numbers of the imaging lens that we are using. Apparently, the law of diffraction is such that the smaller the spatial feature is, the larger its angular span within which the rays, the optical waves, propagate in free space. Now, if the numerical aperture of our imaging lens is limited, only the angles within the numerical aperture of the lens will be captured and translated to an image that is being formed on our detector. And therefore, the smallest spatial feature will be set not by the angular span of the diffraction, but only the part of it that is being captured by the numerical aperture of our imaging lens. And as you can see, the image that on the left is very sharp becomes blurred due to the effect of diffraction. And then the radiation passes the lens and arrives to our detector. On the detector, the intensity of the incoming light has practically an analog distribution in space, but the detector is pixelated. It has many pixels. Those pixels sample this analog distribution of intensity of light. And out of those samples, we want to reconstruct or to know the exact spatial information available in the intensity that arrived to the detector. The reduction of resolution due to this geometry of the detector has actually two aspects. The first aspect is related to Nyquist sampling theorem, and it is practically related to the density of the sampling of the pixels, that the density of the sampling in space of this analog distribution of intensity. The higher the density is, the higher is the analog spatial frequency that we will be able to reconstruct. The second aspect of the geometric limitation of resolution is related to the fact that a Nyquist sampling theorem talks about ideal sampling in which array of Dirac delta functions is involved. But in our case, we have pixels, and every pixel is not a Dirac delta function. Every pixel performs averaging of the intensity of light that arrives to the active area of the pixel, and this localized spatial averaging further reduces the resolution. So this is the geometric resolution limitation. As you can see in this slide, the image we have becomes pixelated and its resolution is reduced. And the third type of resolution limitation is related to signal-to-noise ratio, because every pixel that captured information translated the photons that arrived to this pixel to electrons. And those electrons are given analog readout that is being converted to digital readout by using an A to D, analog to digital converter. And now the question is, what is the quantization noise that we have? Or how many bits of quantization we can allocate to the information of the intensity that is arriving to every and each pixel. The less quantization bits we will have, the lower will be the quality and the resolution of the image that we will capture. And therefore, the dynamic range of the sensor is very important to better represent the image that we capture. And you can see in this slide on the left, this image that was already pixelated due to the geometric resolution reduction, and now it is being sampled with a detector that has very strong quantization noise, such that only a single bit of quantization is allocated to the dynamic range of the intensity in every pixel of the detector. And therefore, the image we have on the left becomes the image on the right, which is even worse in terms of resolution. Now, those are the limitations. How can we overcome those limitations? So as I said in the beginning of my presentation, the point is that the resolution is something related to information in space. But the imager, the imaging system we have, captures information in various domains like time, polarization, wavelength, and so on. And the essence of super resolution is practically a conversion of degrees of freedom. So we need to a priori know which domains of our imaging sensor are available, and we use those domains in order to encode through them some of the spatial information that we have in the object, such that in space we will have less degrees of freedom, and therefore they will pass through our imaging system without being distorted. And then at the detector, we perform a decoding stage. So first we had an encoding of conversion of degrees of freedom, and then at the detector we have a decoding in which we do a back conversion of the degrees of freedom from the domain in which we did the encoding to the space domain, and there the high resolution, the super resolved image is being reconstructed. Now, I'm going to overview in my presentation several types of super resolution techniques. And as I said, different super resolution techniques use different domains to do this encoding, decoding process. One of the most common approaches is to use the time domain to perform this encoding, decoding. Now, whenever you use a certain domain in your super resolution concept, then the technique is called, the name of this domain, multiplexing. For instance, if we use time domain, the technique will be called time multiplexing super resolution. Let us start with, indeed, with the time multiplexing super resolution techniques because they are more common. Let me very briefly explain how it works. You can see in this slide two types of grating. Let us assume that this grating is our object. It has high spatial resolution, but this resolution could not be imaged through our low resolution imager. But if we take an encoding function, which is this grating, the encoding function is a function that we know, and let us assume that this function has as high spatial frequencies as the frequencies we wish to super resolve in our original object. Now, if we put this encoding function on top of our object, what we have here, we have those low spatial frequencies being generated. Those low spatial frequencies are called moire patterns. Now, how come the high spatial frequencies became low spatial frequencies? Because the encoding pattern performed down conversion. Encoding, which was down conversion of the high spatial frequencies available in our object, down converting them into low spatial frequencies. But the object is not a grating. It doesn't have a single high spatial frequency. It has many spatial frequencies, high and low. And therefore, if we do just down conversion like you saw in this slide, then the high spatial frequencies of the object will be mixed. They will be down converted and they will be mixed with the low spatial frequencies existing in the object. And therefore, when we do time multiplexing super resolution, we need to change in time our encoding function. Each time we change our encoding function, we have a different moire patterns. We capture those moire patterns, a set of those moire, time-changing moire patterns. Each of those moire patterns is, when it is captured in our detector, is being decoded by multiplying it with a decoding function which is equal to the encoding function that we use. We sum all those decoded images, and the result is a super resolved image equal, almost identical to the original high resolution object. And why it is called time multiplexing? Because we paid with time. We used the time domain because we captured many images in time in order to perform this encoding decoding process that led to the to the super resolution result. Let us see some examples. Those are some 3 experimental results. You see in the first line 3 types of different objects. This is the reference image seen through high resolution imaging sensor. But when we use low numerical aperture lens, low resolution imaging sensor, those 3 objects are not seen. This is how they are seen. This is the central line. They are low pass. We lose the high spatial frequencies. When we take this low quality imaging lens and we do super resolution, the time multiplexing super resolution I have just explained, this is the reconstruction we get. And we see that the reconstruction resembles very much the original high resolution object. Now, in what I showed you, the encoding function was a grating placed on top of the object, but we don't need to place it physically there. We can project from a distance our encoding function. And the decoding function could be performed digitally by digitally processing our low resolution captured images. In this slide, you see some 2 experimental results applied for microscopy. So you see here 2 images having bunches of cells. You see this image and this image, those are the reference images. But when they are imaged through low resolution objective microscope lens, this is the images we get. The bunch of cells are blurred. You cannot distinguish between the cells. You see they look like one spot, while originally there were, in this case, 6 cells. When we project the encoding pattern, do the time multiplexing and the digital decoding, this is the reconstruction we get. We see that the reconstructed image is indeed super resolved image, that its resolution, it's in space, resembles very much the original high resolution image that we had in both of those experiments. Here you see some additional examples. Again, one object, second object. Those are the reference, those are the low resolution images, and this is the high resolution reconstruction. One interesting thing is to take these super resolution concepts towards nanoscopy. And what we do there, we take a regular microscope and we put metallic nanoparticles. They are nanometric and they are floating in the solution above the object we want to image. Those nanoparticles are our encoding pattern, because the encoding pattern doesn't have to be a grating, it can be a random pattern. The only thing is that this pattern needs to be a priori known to do the decoding, the digital decoding. In our case, we use low concentration of nanoparticles, and therefore they can float while the distance, the average distance between nanoparticles is larger than the size of our point spread function, of our imager's resolution. And therefore, we have a set of moving in time blurred spots. We can, because they are separated, we can localize them, find the center of every spot and construct a decoding high resolution function in which at the center of every blurred spot, we put a point which is the nanoparticle that was there. And we do the decoding and we obtain super resolution. But the resolution in this case is not just better than what the optics allow us, it is even better than the optical wavelength. In this specific case, we got the resolution which resembled the size of our nanoparticles, which was only a few tenths of nanometers. You can see here the resolution target, which you could not see. Then you super resolve with the technique, the time multiplexing concept I spoke with you about, and you see the reconstruction. You can see here another example. This is 3 lines. This is the cross section, how it is imaged without super resolution. You cannot see the three lines, and those are the three peaks in the cross section that you see with the super resolved concept. The point is that when the nanoparticles become very small, the amount of light that is back reflected to the camera is very low, and therefore the SNR is low. And if the SNR is low, our capability of localize the center of every moving blurred spot in order to construct the high resolution decoding pattern, this ability is damaged. And therefore, in order to enhance this ability, instead of illuminating with CW, with a constant light, we modulated the illumination in time. For instance, we took our laser and we modulated it at frequency of 3 Hertz, so it was blinking. And then what happens? All the relevant information which was related to the interaction between our object and the nanoparticle was also blinking at 3 Hertz, and all the noise was not blinking. And therefore, the images look at very low SNR. But if we analyze them in the time domain, we see that at frequency of 3 Hertz, the SNR is very high. So we filter the frequency of temporal frequency of 3 Hertz, and then the contrast, the SNR of our spatial images is significantly enhanced, and we can perform our super resolution, reconstruct the cells, the structures inside the cells. By the way, we can use different types of nanoparticles, illuminate them with different types of lasers, modulate every laser a different flickering frequency, and that way to be able to reconstruct many images simultaneously and have high resolution result in with less amount of time. In order to do this, it's not only that we collect data, but there is a lot of image processing algorithms that speed up. The algorithms are related to those algorithms of localization, of finding the right decoding pattern. And we have developed algorithms related to K-factor algorithm that speed up the regular localization algorithms approximately by a factor of 2 and leads to a 3-dimensional super resolved reconstruction with nanometric of objects with a nanometric resolution. You can see here a construction of 3-dimensional cells. And the nanometric resolution can be as small as the size of our nanoparticles. Now, when we allow the nanoparticles to move by themselves, they move in Brownian motion, and then we do not control their movement. And when we don't control their movement, it takes them more time to scan the full field of view, the full object that we want to super resolve. One of the things to speed up and to optimize the process is to use optical tweezers. So in this experiment that you see here, instead of allowing the nanostructures, the encoding patterns to move by themselves, we shifted them by another optical beam, which was our optical tweezer. So we moved the encoding nanostructures on top of our object and did the same super resolution, but it took us less time because we controlled the movement of the encoding pattern. I spoke with you about time multiplexing, but as I said in the beginning of my presentation, super resolution can use other domains. For instance, colors or wavelengths. In this specific case, you see a wavelength multiplexing super resolution microscope that we have built. This microscope doesn't have objective lenses at all. Instead, after the condenser lens, we place a diffractive optical element that disperses the color, that illuminates our object such that every color arrives to a different spatial location on top of the object, of our inspected object. Those colors are collected to a spectrometer. The spectrometer analyzes the spectral information, and the spectral information, the color information, could be translated to spatial information because the decoding is according to the encoding that we had, which was a lookup table, because every color went to a different spatial location. So we can convert colors to spatial coordinate and therefore convert the spectrum of the captured by the spectrometer into spatial image, like you can see here where we reconstruct experimentally gratings, or here where we reconstruct or image a biological cell. Another interesting direction that we are working on is a micro-endoscopy, disposable micro-endoscopy. we have developed a concept in which we have a micro-endoscope, which is as thin as the human hair, which has large number of tens of thousands of micro cores, optical cores that conduct light and allow us to have very high resolution imaging, while the endoscope is so thin that it is minimally invasive when it goes into the biological tissue. For instance, in this case, we do imaging from inside the blood artery and see its partial blockage. We have endoscopes as thin as human hair, about 100, 200 microns, that's all. But their resolution is very high. It's better than resolution of very big and thick conventional endoscopes with resolution of hundreds of thousands of pixels. You can see here example of images that we get with our micro-endoscope. Here we did brain surgery and extracted images from deep cortical layers within the brain. We see blood vessels inside the brain. Because the endoscope was so thin, we could go inside in a minimally invasive way. One of the problems that you have here is the fact that there is a lot of blood and you need to image through blood, through scattering medium. We applied this wavelength multiplexing super resolution concept I told you a few slides ago in order to improve resolution and allow imaging through blood, through scattering medium. You can see here one experimental result. This is how the reference look like. This is how the reference look like through blood. You don't see the lines. And here you clearly see the lines which are captured with our wavelength multiplexing concept of super resolution for imaging through scattering medium. There are many more techniques. The time is very short, so I will not go into them. For instance, here we do coherence multiplexing super resolution, and here we do field of view multiplexing super resolution. So there are tens of techniques, hundreds of research papers that could benefit many, many fields involving imaging, endoscopy, biomedicine, and so on. The second part of my talk in the next 5 minutes is going to speak about ophthalmologic devices. And specifically, I'm going to speak with you about the problem of presbyopia. Presbyopia is the lack of capability of the lens of our eye to do accommodation. And we have developed special technique to extend the depth of focus of the imaging lens, any imaging lens, which can be contact lens, which can be spectacles, which can be intraocular lens. We extend the depth of focus significantly, as you can see here experimentally. So this is without extending, and this is when extending. You see that the depth of focus is very long, and it is all optically obtained over a full field of view. And therefore, if you have depth of focus sufficiently large, you don't need anymore the accommodation capability, because everything is in focus from near to far in a continuous way. And people don't need to use progressive lenses or multifocal lenses or multifocal contact lenses or intraocular lenses. You can see here experimental result. This is regular lens. This is a zoom of this region. Far away, you have focused image, but the business card is blurred because it is not in focus. We add the scratches that extend the depth of focus of this lens, and you see clearly the remote objects focused. And now the business card is also focused, and you can read the details of it. We applied it for ophthalmology, for contact lenses, spectacles, and intraocular lenses. You see how those patterns, those scratches look like, the scratches that enhance the depth of focus of the imaging lens. You see how a defocused image, ophthalmic image, looks like with our lenses. We did many clinical trials with it, again, for spectacles, contact lenses, and intraocular lenses. I will give you very short examples because the time is very, very short. Here you see example of an intraocular lens. This is regular lens that is bifocal. It's called Restore. It's a commercial lens that gives you good focus for remote objects, good focus for near objects, but everything in between is blurred. In our case, with extended depth of focus intraocular lens that we have here, everything is continuously focused over the full field of view from near to far. So far is focused, intermediate is focused, and near range is also well focused. So this was intraocular lens. This is our contact lenses. You see one of the subjects participating in the clinical trials wearing our contact lens. Those are the scratches. Those are his eyelids. This is clinical trials we perform. This is PVMF-HA, is pure vision multifocal high edition contact lens. It's a bifocal contact lens, very commercially sold. And this is our lens. And you see that the commercial lens, which is one of the most common lenses that is bifocal, it is used to solve presbyopia. And this is our lens. You see that our lens in this clinical trial performed about 3 times better than the commercial, most commonly sold bifocal contact lens. You see the results not only for soft contact lenses, but also for rigid contact lenses. Again, near and far well seen. In other solutions, the images are blurred. One of them is blurred. There is another thing which is called the halo effect, which means how the lens is functioning at night when you have very bright point sources like lamps and so on. And our lens not only extends depth of focus and solves presbyopia and actually also other problems like astigmatism, but it has also significantly reduced halo effect, and therefore our subjects could enjoy it much better at night, at dark conditions. You see here our lens and its halo effect, the point source that is being imaged, very similar to a monofocal lens, while for instance a spherical rigid RGP rigid contact lens has very strong halo effect, which doesn't allow people to see at night. I will finish with this slide saying that the extended depth of focus approach that I showed you, which is an interference-based, it is a unique solution because it is more energetically efficient and it has no chromatic aberrations. It doesn't have to be used only for ophthalmology. One of the directions that we tested it for is, for instance, in microscopy, at high resolution microscopy, where we could see by adding it to the objective lens, we could see better with our microscope. For instance, this is extended depth of focus objective lens. This is not extended depth of focus lens. So in the non-extended depth of focus, you see 2 cells, E. coli cells, all the rest are blurred. In our case, everything is in focus. So again, another example, you barely see something without the depth of focus extension. In our case, you see much more details because everything is in focus at much larger axial distance. So I will end up my presentation here and answer your questions if there are any. Thank you for your attention and time.